Have you ever used bleach to disinfect a surface or chlorine tablets to purify water? Ever wondered why elements like chlorine are so reactive, especially with metals? Well, that's the magic of electron affinity, a property that reveals how eagerly an atom accepts an extra electron. Let's dive into the microscopic world to explore this powerful periodic trend. First, atomic size. This is inversely related. As atomic size increases, the nucleus is farther from the valence shell, reducing its ability to attract an electron. That's why larger atoms have lower electron affinity. For example, oxygen, being smaller, has a higher electron affinity than sulfur, even though both belong to the same group. Next, nuclear charge. This is directly related. A greater nuclear charge increases the pull on incoming electrons, making electron acceptance more likely. Finally, effective nuclear pull. Smaller atoms with high nuclear charge, like fluorine, can strongly attract electrons, giving them very high electron affinity. In general, electron affinity increases from left to right across a period due to decreasing atomic size and increasing nuclear charge. However, there are exceptions. In group 2 and group 15, elements like beryllium and nitrogen deviate from this trend because of their stable electronic configurations, with completely filled and half-filled subshells respectively. For example, carbon has an electron affinity of minus 1.25 eV, oxygen is minus 1.48 eV, and fluorine is minus 3.60 eV, clearly showing the increase across the period. Neon, a noble gas, is an exception with zero electron affinity because its stable octet leaves no room for additional electrons. Finally, electron affinity reaches its peak in halogens like fluorine, which need just one more electron to achieve noble gas configuration. Now let's move down a group. As we descend a group in the periodic table, atomic size increases. Each successive element has an additional electron shell, pushing the outer electrons further from the nucleus. This increased distance and electron shielding reduce the nuclear pull on incoming electrons. Hence, electron affinity generally decreases down the group. Let's examine the halogen group. Fluorine has minus 3.60 eV, chlorine has minus 3.80, bromine has minus 3.50, iodine drops to minus 3.20. Surprisingly, chlorine has slightly higher electron affinity than fluorine. Why? Fluorine is so small that the repulsion between its electrons is significant. Chlorine's larger size helps accommodate the extra electron better. Greater electron affinity means a stronger tendency to attract electrons in a bond, which is why electron affinity is directly linked to electronegativity. Halogens like fluorine and chlorine are extremely reactive due to their high electron affinity, making them essential for disinfectants and bleaching agents. Metals such as sodium have low electron affinity, while nonmetals like fluorine have high electron affinity. This explains why metals tend to lose electrons and nonmetals tend to gain electrons in reactions. In industry, elements with high electron affinity are crucial in redox reactions, electrochemical cells, and even as oxidizers in rocket fuel systems. So, what have we learned about electron affinity? It is the energy released when a gaseous atom gains an electron, a property that varies across the periodic table based on atomic structure. Across a period, electron affinity generally increases due to decreasing atomic size and increasing nuclear pull. Down a group, it usually decreases because atoms grow larger and shielding reduces the effectiveness of nuclear attraction. We saw exceptions like beryllium, nitrogen, and neon, where stable configurations make it hard for the atom to accept electrons. And we explored how electron affinity connects to chemical reactivity, bond formation, oxidizing power, and even real world applications, from chlorine in pools to oxygen in our bodies. I hope now you see how this periodic property is not just a number, but a window into an atom's personality and behavior in reactions. Catch you in the next class where we uncover another property shaping the periodic table. Until then, keep questioning, keep experimenting, and keep loving chemistry.